In today's class, we will study Module 5. Module 5 contains the loop antenna, horn antenna and other types of the antennas. Now let us first consider the loop antenna. The loop antenna is the one where we are forming a loop by the transmission lines or the coaxial cables, and the size of the antenna is decided by the area occupied by the antenna. So let us consider these particular figures. So figure number A is a triangular loop, figure number B is square loop, and figure number C is circular loop. And here closely if you consider here, so the antenna is formed in the form of a triangle and each side is having a length A, and each side acts as an one antenna elements, and so this antenna is fed through these particular lines, that is the voltage or the current what you are applying to the antenna will be fed through this point. Whereas in case of square loop, the antenna is arranged in the form of a loop. For a square loop, where the antenna is formed in the form of a square and each arm is having a dimension of A, and the antenna is fed through this particular point. Here each side acts as one antenna elements. I mean to say, for a square loop is considered, we have 4 antenna elements: element 1, element 2, element 3 and element 4. Similarly, this is circular loop where the antenna is formed in the form of a circle which is having a radius A, and the signals are fed through these particular points. And depending upon the area occupied by the antenna is classified as a small loop antenna or the large loop antenna. If the area occupied by the antenna is less than lambda square by 100, where lambda is the wavelength, so then the antenna is called as a small loop. If the area occupied by the antenna is comparable with the wavelength, so then it is called as a large size antenna. In order to understand the function of the loop antenna, so let us consider a square type of the loop antenna. Here the antenna elements are arranged in a square form and each side acts as one antenna elements, and so this antenna element and this antenna elements are similar, and this antenna elements or this antenna are similar. I mean to say, these two antenna elements act as a vertical antenna elements, and these two elements act as a horizontal antenna elements. So the same antenna, so we are representing in this particular form, that is in the rectangular form, having the dimension A and A, that is length is A and the breadth is A. Now, so this antenna we are placing in the coordinate systems, where so this is element 1 and this is element 2, and this is element 3 and this is element 4. Element 1, element 2, element 3 and element 4 are the basic antenna elements what we have studied. Now, so this is placed in such a way that it makes an angle theta with the z-axis. As we know, the antenna radiates both in the vertical plane and in the horizontal plane. Now, we want to observe the radiation produced by this particular rectangular loop antenna at the point P. P is the point where we want to measure the signal strength of this particular antenna, and E, H indicate that at this particular point we are having both electrical field component and the magnetic field component. Then, so the radiation pattern produced by these 4 antenna elements, that is 1, 2, 3 and 4, is looking like this. That is, so this particular pattern is the radiation pattern due to the element 1 and 2, and this is the pattern due to the element 3 and 4. That is, whatever the patterns we are getting along x 0 degree and 180 degree, it is due to the antenna element 1 and 2, and whatever the pattern we are getting along 90 degree and 270 degrees, so these are due to the element 3 and 4. Now, the same diagram, it has been represented here. Okay. For simplification purposes, we are considering only 2 antenna elements here, that is antenna element 1 and 2. So, this is the point P where we want to measure the signal strength, which contains both electrical field component and the magnetic field component. And whenever these 2 antenna radiates, they radiates both in vertical direction and the horizontal directions. So, therefore, so the vertical angle we are taking it as theta, and the horizontal angle we are taking it as a phi. if E phi 0 is the field produced by the individual elements of an antenna, then we need to find out the total field produced by the entire loop antenna. Then the total field produced here is E phi is equal to minus E phi 0 into e to the power j psi by 2 plus E phi 0 into e to the power of minus j psi by 2. And E phi 0 is a common, we will take it outside, then e to the power of j psi by 2 plus e to the power of minus j psi by 2. So this we can write it as minus 2j E phi 0 into sin of psi by 2. So this equation, it is in the form of e to the power of j theta plus e to the power of minus j theta divided by 2j. Therefore, if I rewrite this one, then e to the power of j theta plus e to the power minus j theta is equal to 2j sin theta. So therefore, by matching this equation with the standard trigonometric form, we are writing the equation for E5. Let us call it as equation number 1. Psi is equal to dr cos phi. So this is equal to 2 pi d by lambda cos of phi. Sin phi equal to sin of 90 minus theta and cos phi is equal to sin theta. Hence, psi equal to 2 pi a by lambda sin theta. Sin of psi by 2 equal to sin of psi a by lambda sin theta. Since the area of the antenna is less than lambda, or the size of the antenna is less than the wavelength of the signals, less than 1. Based on these conditions, hence approximated by, since a is less than lambda and pi a by lambda is less than 1, hence approximately sin of pi a by lambda sin theta, we can write it as pi a by lambda sin theta, call it as equation number 2. And E phi 0, that is field produced by the individual element, is equal to the field produced by the individual element E phi 0 equal to j 60 pi into I into A divided by R lambda. Then substitute the equation number 2 and 3 in equation number 1. If you substitute equation number 2 and 3 in equation number 1, then E phi equal to 120 pi square I sin theta into A by lambda square divided by R, and where the area equal to A square, because each individual sides are having the area. So area equal to A square. Hence H theta is equal to E phi divided by 125. Then H theta is equal to pi of phi sin theta into A by lambda square divided by lambda. Now these two equations, E phi and S theta, these equations can be used to find, so the field due to the loops of any shape for the area A is less than lambda square. Using this equation, you can find the electrical field component and the magnetic field component of any shape, that is triangular, circular, rectangular, square, etc. If a system consisting of n number of terms, then the total field assuming a uniform current distribution is E phi dash equal to n into E phi. That is, if a system consists of n number of elements, then the total field will be increased by n times. Therefore, E phi dash is equal to n into E phi and H theta dash is equal to n into H theta. let us analyze the loop antenna as a general case. So, that is, consider a general case of uniform current and in phase signal is fed to the antenna, and the size of the antenna is not very small compared to the wavelength lambda. Since, so this particular loop antenna is placed along the xy plane, the only component so that can be obtained is DSI for each element. That is, so whatever the antenna element is there, it is placed along the xy plane, and therefore only component what you are getting is d into a phi for each antenna elements. dA theta is equal to dAr equal to 0, and dA theta is given by dA theta is equal to mu into dm divided by 4 pi r, where so dm is the current moment due to one pair of elements. Now, the phi component of the retarded current moment, so due to one element is I of A d phi cos phi, where I is equal to I0 into e to the power of j omega into t minus r by c is being the peak current produced in the antenna elements. What all this particular thing is indicating is that here we are considering a pair of elements. Here I am having one antenna elements and here I am having one antenna elements. Each antenna elements are having a length A, and this is the point P, or this is the point P where we are measuring the signal strength, and current flowing through this particular antenna is I0. Because the antenna radiates in both in the horizontal direction and the vertical directions, we are considering the angle theta and also we are considering the angle phi, and because the antenna elements are placed like this, the signal from this particular antenna element reaches earlier than the signal from this particular element. So, because of the path difference, so this path difference is equal to 2 Ba cos phi sin phi. So, this is equal to psi. referring to the XZ plane, the resultant moment dm at a large distance due to a pair of diagonally opposite element is, that is, the antenna is placed in the XZ plane, and referring to this particular XZ plane, the resultant moment dm at a large distance due to a pair of diagonally opposite element is, that is, we want to find the field at a point P due to diagonally opposite element by referring to the XZ plane. Then dm equal to 2j I of a into d phi cos phi sin of psi by 2, where psi equal to 2ba cos phi sin theta. Therefore, so dm equal to 2j I a into cos phi sin of ba cos phi sin theta into d phi u, call it as equation number 7. Substitute this equation number 7 in equation number 6. Then a phi equal to j into mu of phi into a divided by 2 pi into r, and integration from 0 to pi sin of beta a cos phi sin theta cos phi d phi u. If you integrate this particular equation, then a phi is equal to j mu I of a divided by 2r j1 ba sin theta, where the j1 ba sin theta is the Bessel function of the first order, and the argument ba sin theta is given by j1 ba sin theta equal to 1 by pi 0 to pi sin of ba cos phi sin theta cos phi and d phi u. And the far electrical field has only one component given by Er equal to E theta equal to 0 and E phi equal to minus j omega into a phi u. Substituting the a phi u, then E phi equal to mu into omega divided by 2r, so j1 beta a sin theta, or E phi is equal to 60 pi ba I divided by j1 beta into sin theta, call it as equation number 9. And we know that h theta is equal to E phi divided by 120 pi. Therefore, h theta is equal to beta a divided by 2r into j1 into beta a sin theta. So, these two equations will give you the electrical and the magnetic field component at a far distance r from the antenna.